Lab 4, the physics of extreme sports. The goal of this lab was to observe the motion of the spring mass system and compare it to a computational model in order to show that it obeys the laws of the energy principle. I observed a mass of 0.42 kilograms moving in an elliptical orbit while oscillating on the spring, and predicted its motion using Newton's second law and the energy principle. My results were that I found the predicted oscillation motion graph that accurately represents the motion in the observed data. In this lab, we use Newton's second law of finding the force of a spring. The force of a spring is K times S final minus S initial, K being the spring constant, S final being the final position of the spring, and S initial being the equilibrium position. We also use Newton's second law of finding the force of gravity, the force being mass times gravity. This is my visual from Tracker, which shows the spring mass system oscillating along the specified x and y axis, which is placed at the fixed point at the top of the spring. The mass of the object was given as 0.402 kilograms. From Tracker, I was able to obtain the x and y position versus time data and was able to calculate the initial conditions and interpret the graphical results to later compare it to the computational model. I then saved this data onto an Excel spreadsheet that would be used in my computational model later. From Tracker, my initial position was 0.003 in the x direction and negative 0.703 in the y direction. My initial velocity was 0, and the mass of the object was 0.402 kilograms. To find the period, I used the equation t equals 2 pi times the square root of mass over the spring constant and manipulated it to find the spring constant. I was able to find the period t by observing the graph from Tracker and observing the change in time for 5 oscillations and then converting that to the time it took for 1 oscillation. From this, I was able to calculate the spring constant. In order to calculate L, the spring length, I used the force of gravity is equal to the force of the spring. This means that mass times gravity is equal to the spring constant K times the stretch. The stretch can then be calculated by manipulating this equation, and since I knew the stretch and I knew the relaxed length, which was 0.7 meters, I found L, which was 0.022 meters. The energy principle was then further used to calculate energy changes. We know that delta E, or the change in energy, is equal to 0, and therefore delta E, which is also the kinetic energy plus the potential energy of the gravitational plus the potential energy of the spring, is equal to 0. The kinetic energy is 1/2 mv squared. The gravitational potential energy is the mass times gravity times the change in height, and the potential of the spring is 1/2 the spring constant times the stretch squared. We were then able to calculate the energy changes. Delta K, or the change in kinetic energy, is the final kinetic energy minus the initial kinetic energy, which is equal to 1/2 times the mass times the final velocity squared minus the initial velocity squared. The change in gravitational potential energy is the final gravitational potential minus the initial gravitational potential, which is equal to the mass times the gravitational constant times the final height minus the initial height. Lastly, the spring potential energy is equal to the final spring potential minus the initial spring potential, which is equal to 1/2 K times the change in stretch squared. The spring mass system shows the orbital motion that it rotates in. The black arrow represents the force of gravity, and the blue arrow represents the force of the spring. The computational model represents the graph of the energies of the oscillating system. The blue line represents the change in kinetic energy, the red line represents the change in the spring potential energy, the green line represents the change in gravitational potential energy, and the yellow line represents total energy, which we can see is approximately around 0. When comparing the predicted versus the observed model, the blue line represents the predicted and the red line represents the observed, or from Tracker. Discrepancies in the data could be due to any error when specifying the center of mass on Tracker and any other small forces that could have been acting on the system. Discussion question 1 asks, is my model for the energy principle satisfied? I can see that the total energy is the yellow line, which remains 0 and constant, and therefore proves that there is no change in the total energy and that energy is conserved. Discussion question 2 asks, using the data obtained in Tracker, make 2 separate estimates of oscillation periods. First estimate from the x position and then estimate from the y position data. Compare the 2 estimates and then discuss. By observing the number of oscillations and the time differences for the x and y positions, I was able to calculate that the period of oscillation from the x was 1.6537 and the period of oscillation from the y was 1.54. Since the spring is constantly changing directions, the periods of oscillation were different, and you cannot use these to estimate the oscillation periods. Instead, we had to use data from the video where the spring is only moving in the y direction. In conclusion, the spring mass system abides by the energy principle. All of the energy is conserved in the computational model